Okay, so this is going to be section 2.5 to section 2.5, which is linear functions and models. So we've already talked a whole lot about graphing functions, right? That's kind of been like the theme for the past almost 2 weeks, right? Graphing functions, and we haven't really graphed any linear functions yet because we've been so involved with like the x squared, x cubed, square root of x, cube root of x, 1 over x squared, 1 over x, all those different types of new functions, right? So let's talk a bit about linear functions, which are going to be very familiar because you already know how to graph linear functions. And also, let's talk about some models, some linear models that can be used to solve real life problems. And by real life problems, I mean like word problems, right? How do you translate a real life problem into the context of math? You got to make it a word problem, right? Sorry, my camera's going crazy. Why is it not focusing? It's like focused right here. Wow, that's great, camera. You can give me tons of detail right there, but maybe if I just start writing, let's see, 2.5. So a linear function is going to be of the form f of x equal, no, it's still not. All right, give me 1 second. And I can't even pause the video to fix this. All right, let me see, settings. Come on. There we go. Okay. All right. Hopefully it's going to behave. All right. So f of x equals. Now you're used to seeing it as mx plus b, but I'm going to write it as ax plus b because that's what the text does, and I don't want to deviate too much. But just know, I mean, it doesn't really matter. Later, we're going to write quadratic functions. In chapter 3, we're going to go in a deep dive into quadratic functions, and we'll use a, b, and c for the coefficients there. So it kind of makes sense for linear functions to use, those first alphabet letters. So we have a linear function of the form ax plus b. Okay, we can think of a, so that number a there, as the slope of the graph of f of x, because it is the slope. It is a measure of the slope. B is the y-intercept of the graph of f of x. So if I was to draw some generic linear function with slope a and y-intercept b, well, I wouldn't know exactly where to put it and how to tilt it. But I could say, hang on, let me see something here. Why does this look tilted? Sorry. This looks tilted. What happened to my camera? Is that better? I think that's better. Okay. So how do I represent A and B? Well, B is easy. B is the y-intercept. I can literally point to it right there. B is the, well, I should really say the y value of the y-intercept, because the y-intercept is a coordinate point, 0, some number, B, right? So B is the y value. B is the y value of the y-intercept. Now, what about slope? What about slope here? Slope is a measure of, so remember your slope formula. It's a measure, it's a ratio, it's a measure of how much the graph is changing vertically versus how much it's changing horizontally, right? So given some point here and some point here. So some point here being, x1 comma y1, x1 comma y1, and some other point over here being x2 comma y2. So just subscripting one for the first point and two subscript 2's for the second point, then slope is the ratio of this side length, y2 minus y1, divided by this side length, x2 minus x1. So slope is literally how tilted the line is. Now, I think I'm going to have to throw this brown marker away. I'm going to swap to the next darkest color I have left until I get some more black markers, which are the best because of the obviously contrast on the white paper. So for now, I'll use this purple marker. Now, I can also, in the context of a word problem, i.e., when I'm making models, so in other words, when I'm making models out of a word problem, in the context of a word problem, A, the slope, is the rate of change. Is some linear rate of change. Okay, that'll be more clear when we actually do some problems, some modeling problems. In the context of a word problem, B is the initial amount. Okay. Let's go straight for it. I'm going to go a little out of order with the textbook here. I want to talk about modeling first, and then we'll go look at some problems that deal with like the properties of linear functions and like, different things. We can talk about parallel lines and perpendicular lines and all that good stuff that comes up when you talk about linear graphs at this level. So example 1, let's go straight for it. Water is being pumped into a swimming pool, at a rate of 5 gallons per minute. That's 5 gallons per minute. That's a rate, right? Remember what a rate is. It's a fraction that measures the difference, rather it measures two quantities that are unrelated, that have unrelated units like gallons per minute, or it could like speed as a rate, right? Like distance per time, miles per hour, meters per second, stuff like those are all rates. And this is a rate of gallons per minute. Okay, initially, the pool contained 200 gallons of water. All right. Part A of this problem says find build, I would say, they say find, but I would word it as build a linear function. This is okay. Find a linear function, and let's call it V. Why am I calling it V? I'll explain that models. What am I modeling? The volume of water, the amount of water, right? The volume of water in the pool at time t. Okay, so the name of my function is going to be v. So when I write it down, it's a function of time, right? Okay, so let me back up a bit. It's v stands for volume. Volume is the amount of like something, right? Just, well, it's the amount of space that's being taken up by something. In this case, it's water, and our measurement for volume is in gallons, and our measurement for t, time, is in minutes. And how do I know that? Well, because the rate was given as gallon per minutes, or gallons per minute, rather. So when I write my function here, I already have my name given. It's v of t, right? Volume is a function of time. Sorry, my voice is already going out. Volume is a function of time. What does that mean? The volume in the pool, the volume of water in the pool, depends on how much time has passed. All right. Now, I know this is a linear function because there's a linear rate here, 5 gallons per minute, and there's also an initial value of 200 gallons. So how do I relate these things, and how are they involved in my function, and how are they related to t? Well, initially, I'm going to have 200, right? That's an initial value, and it's going to get added to however much water is being pumped into the pool. So this is my initial value, no t value, no t attached to it, right? Because it's already measuring volume. It's already measuring gallons, which is exactly what I want this to measure. Now my 5 is a rate, right? It's in gallons per minute. So I cannot write, this is not correct yet, right? Because this is a rate. What do I need to attach to this in order for this to yield a measurement of gallons, which is exactly what I want here? I need to attach time there. So 5 is my rate here, and 200 is my initial value. And if you step back from math class and said, you know, if I said, look, there's already 200 gallons in there, it fills up 5 gallons per minute, and we have to fill it up, you know, 1,000 gallons. How long will it take? Well, then you would know how to figure that out. Like if you really stepped out of math class, you could probably figure that out like intuitively. All we're doing here is just placing a model onto it. This is called a model. Whenever you build a math equation or a function or any mathematical object to mimic something that's happening in real life, we call it a model. So this is a linear model because it's a linear function. Now, if you like, you know, we tend to put that term that has the rate attached up front, you know, so this might be a more comfortable way of writing it. So my rate of change is 5 and my initial value is 200. Part B says, what does it say? If the pool has a capacity of 600 gallons, so let's say the pool capacity of 600 gallons. Of course, I'm going to say, how long will it take to fill up? Okay, so I want that maximum capacity, the fill point is 600 gallons. That's where I want its volume to be. And I'm going to try and solve for the time. So I want volume, this is volume, V of t is volume, to be equal to 600 gallons. So I'll replace this with 600. Literally this V of t gets replaced by 600 because that's where I want the volume to be. And I just set it equal to my linear function here. My volume is 600 gallons. They're giving me the output of the function here. They're giving me the output of the function and asking for the input. And this is how you set that up. You literally replace the name of the function, which is standing in for the output, replace it with 600, and now we're going to solve for t. Okay, so just a little bit of algebra there. And we figure out that it takes 80 minutes. 80 minutes. That's how long it takes for the pool to fill up. 80 minutes. If it has a capacity of 600 gallons, that is. Now, let's say that we are filling it up and we left the hose on and went inside to get lunch and forgot about it. We say the pool has been filling up for 2 hours and it has a capacity of 600 gallons. How much water was wasted? This time I'm given an input. Time is the input of this function, right? Time is the input of this function, and I'm given time, and I'm asked for a volume indirectly, right? But I am asked for a volume. So I'm going to say V of, do I say 2 here? T is equal to 2, right? No, because this is measured in hours. Our time for our function is measured in minutes. So I'm going to say V of 120 for 2 hours is equal to 5 times 120 plus 200. So you have to make a note here that 2 hours equals 120 minutes. That's why I'm plugging in 120 into my function. And bear in mind that this is just a little placeholder for the output that this is going to give me. So order of operations here, so I'm doing 5 times 120 first, which is going to be 600. And that's giving me 800 gallons. This is measuring gallons. All right, that's not the answer to the question, though. The question was how much water was wasted. Well, the pool has a capacity of 600 gallons. So we wasted 200 gallons since 800 minus 600 is equal to 200. So that 200 was excess. That was excess. So it only takes 80 minutes to fill up, but we accidentally left it on for an extra, 40 minutes, which gave us an extra 200 gallons that are just like excess, like leaking out of the pool into the ground or whatever, overflowing, right? Okay. So that's an example of how you can take a real world situation, build a linear function out of it, and then answer questions about it. And there's really only 2 questions that can be asked. Either you are given the output and asked for the input, which is what happened in part B, or you're given an input and asked for an output. Right? It's either one or the other, really. You're either plugging in and evaluating, or you're setting it up and solving for the input. All right. Let's do a little bit of some of this boring stuff. Let's get this boring stuff out of the way about, like I said, some more of the construction of linear function. Not the construction really, but just some details. In fact, let's just talk about identifying linear functions. All right. Let me write these down. Okay. So only one of these is not a linear function. Let's talk about this. Oh, hang on. Is my camera being cut off? No, all right. So part A clearly is a linear function. I mean, it's like exactly of the form I gave, except the A and B, AX plus B are kind of flipped around. Linear, it's linear. And let's go ahead and note with A equals 3 and B equals 2, where I'm citing this form f of x equals ax plus b. That's what I'm referencing when I say A is 3. So 3 is the slope of this. You could call it the slope of this linear function if you were talking about the picture of it. You could call it the rate of change also. And B is 2, which you could call the y-intercept, or rather the y-coordinate of the y-intercept. Or you could also call it an initial value. All right. How about part B? As in this question, g of x. Yes, it's linear. It's linear with, now we need to be careful here. Let's note that g of x can be written as 3 minus 6x, and that's how we need to write it in order to identify A and B. So A is equal to negative 6, the number attached to the x, negative 6, and B is equal to 3. So anytime you see something like this, where there's a number outside, you need to clean it up and get it as just two terms, this term and this term. Order doesn't really matter. You can flip it around and put the x term first if you'd like. If you did that, it would look like that, negative 6x plus 3, the negative sticking with the 6. The 3 is positive, so when we rotate them, we should have plus 3 there. Hence why B is positive 3, A is negative 6. Okay, let's look at part C. H of x is not linear. Not linear. It's the only one that's not linear. Why do I say that? Well, it's actually quadratic because if I multiply that x through, I get 4x plus 3x squared. That's not linear. So the defining feature of a linear function, well, at least in this context, what contrasts this to a linear function is that the highest degree for a linear function, the highest exponent on the x's should be a 1. And remember that all of these have an understood 1 on the exponent of the x. Right, 1. This one though, that 2, that's the problem. That's the problem right there. If we graphed this, it would not be a straight line. It would not be linear. It would be some parabola. Can we graph, by the way, just throw back to 2.6 when we were graphing all the parabolas and whatnot. Can we graph this? Well, not exactly, because it's not exactly of that form where we have like a number added to the outside of the function because of that x right there. That x throws a wrench in the plan that we had from 2.6, but we will learn how to graph this in the next chapter where we go in a deep dive about quadratic functions. Now, D is linear. And how do we identify A and B here? Because it's of this fractional form here. Well, note that K of x can be written as 1 over 4 minus 5 over 4 times x. If you split the fraction, which is it's a legitimate thing to do. So A here is the number attached to x, so negative 5 over 4, and B is 1 over 4. Ugh, 1 over 4. Oh, I forgot the word and. There we go. Okay. That's just some of the vocabulary example out of the way, right? Making sure we know what a linear function should look like algebraically. All right. Let's make sure we know how to graph. What was that? What did I call that example 2? Let's say example 3. Start with an easy one. F of x equals, let's do that 3 plus 2x one, or it's 2 plus 3x, whatever. This is fine. All right. F of x equals 3 plus 2x. So how do we graph this real fast without having to make a table of values or anything? We say, all right, we're gonna draw a little graph, and we say, let's go, I don't know, do we know what we should go out to? Maybe not. We may need more tick marks. We may not even need this many at all, but I'll just go to 6 in each direction. Oops. All right, so how do we graph this? We say, well, its y-intercept is 3. So an initial value is 3 when x is 0. When this horizontal input value is 0, the output is 3. The output is up at 3. So that's coming from this number here with no x attached to it. And then my slope is 2. And recall that recall that slope is a measure of vertical distance over horizontal distance, right? It's a measure of how much the line is changing vertically versus how much it's changing horizontally. In other words, you can think of the 2 as a 2 over 1 if you write it as force it into fraction form. And you can think of it as vertical displacement, or vertical change, I guess, over horizontal displacement. There's so many different ways to describe this. You could also call it as a what's it called? Rise over run. It's like the most, I guess, like layman's terms way to say it. Rise over run. So starting from this point, I go, the vertical displacement is 2, horizontal is 1. So I go up 2 over 1, and then I connect the dots. Because how many points do you need to define a straight line? You only need 2. What value should it go through here on the x-axis, by the way? Like how do I know? Like, it doesn't really matter. Once I have these 2 points, I could just go ahead and sketch it, right? But if I wanted to be particular and say, what values is it supposed to go through over here? So what if I wanted to ask that question? Let me write that down. Let me say it this way. Where remember how to do that? Where does the line cross the x-axis? That's a question of where. That is the same as where is its x-intercept. How do you find an x-intercept? Set y equal to 0 and solve. What is y here, though? Right? What does that mean? Well, y is represented here by our function, right? So we say, like, when we just wrote these functions, or rather these lines, as y equals mx plus b, like that was the algebraic form we had, y equals mx plus b. The y value was sort of playing the role as output, right? Now we have this f of x notation playing the role of output. So now we're going to set f of x equal to 0 and solve. I mean, the math doesn't really change. It just looks a little different for the setup. So if we were to do this, we would say 3 plus 2x is equal to 0. Literally replacing that output with 0. 3 plus 2x equals 0. What is that going to give me? That's going to be 2x is equal to -3. And then x is equal to -3 over 2. And what is that, by the way, as a decimal? Because maybe it'll be helpful to have it as a decimal. -1.5. So my line should end up going Yeah, everyone. My tick marks aren't right. It should end up going through right here, right? Because that's where x equals negative 1.5. But my tick marks are all wacky, so well, should be more like that. Of course, if I actually was really careful about how it really shouldn't have been that bad. I think it's just because these tick marks got a little away from me there. So if I wanted to make a really nice graph, you can probably skip through this part of the video. Don't have to watch me making all these tick marks. Okay, so initial point at 3, 0, I go up 2 over 1. Remember that if I want another point, I can go down 2 over 1 this way. Point should be there. And then it'll go through the just like that. That's a bit better. That's a bit better. Now, do you have to do this every time? No. All you have to do is find the y-intercept and then one more point using the slope, find one more point, and then connect them. But sometimes it's helpful to know where the x-intercept is. What about that other weird one? Yeah, let's graph that one. So I'm going to call this part B, this is example 3, part B. K of x equals 1 minus 5x over 4. So recall that we were able to write this as negative 5 over 4x plus 1 over 4. Just by splitting the fraction and then flipping it around. Okay, so if I go to graph this, I've got fractions to graph, but that's okay. I think I can manage. So So I'm looking at that slope, 4, 5, 6, 2, 3, 4, 5. Looking at that slope, and I see that rise over run is negative 5 over 4. That's telling me when I see negative 5 over 4, I'm thinking down 5 and then right 4. Or I could go up 5 and left 4, kind of sticking that negative in the denominator. So these two are the same two different ways to interpret the same, just two different points on the same line. So either one of these is legitimate. But the first value I'm looking at is that y-intercept at 1/4, so it's like really close. It's like right there, close to 0, and 1/4 right there on the y-axis. So that coordinate point is 0, 1/4. That's 0, 1/4. Now I see that I should go down 5 and right 4. So as I go down, I want to make sure that I'm not going all the way down to -1, right? I'm going a little bit before it. Going a little bit before it. So 1, 2, 3, 4, 5. Okay, so I should be somewhere along, like right above this tick mark here. And I want to go over 4. So somewhere out here. 1, 2, 3, 4, 5. So somewhere out here and there, maybe. Let's see, I'm not quite lined up. There we go. There's one of my other points. And that's enough for me to graph this. But I'll give you another point just so you see how you could use this to find another point on your graph too. So I can go up 5 and left 4. So if I go up 1, slightly above each of these tick marks, right? 1, 2, 3, 4, 5, and then left 4 right there-ish. Let me get lined up and make sure I'm looking at it from the side. Yeah, that looks good. And then I can connect all 3 of these. And there's my line. And again, that point there, 0, 1/4. Okay, so that's graphing a couple linear functions. Okay, let me see what else the book says. What else do we have? Let me make one final note, and then I'm going to see if there's maybe any homework problems I should look at. Just want to make one final thing here. Consider f of x equals, let's say -3x plus 4. Just want to point something out, just reiterate. I already said this in words, but I'm going to completely write it down. The slope is -3. The rate of change what is the rate of change? The rate of change oh, sorry, got distracted. The rate of change is also -3, right? It's also -3 because the rate of change is the slope. The y-intercept is 0, 4. So the y value of the y-intercept is 4. Y value of the y-intercept. And the initial point is 0, 4. We might say depending on what the problem is, I could say like the initial value is 4. So that's just getting into some semantics here, but like the initial coordinate point, if there was a starting coordinate point, it would be 0, 4. Like literally that's where you would start if you were going to graph this function. If this was representing some model, like, you know, like the swimming pool example we did, then you would call it an initial value, maybe like an initial amount of water or something like that. All right, now let me go to WebAssign. I wish I could pause these videos, but when I record them in Teams, just in case I need to share my screen, and doing that means I can't pause the video. Normally I would pause so you don't have to watch all this, just like waiting for me to do something. All right, logging into WebAssign. Oof. All right, let's go to 2.5. A lot of problems in 2.5. Okay, got some problems to look at. Let's just let's do this. Find the slope from the graph. I'm looking at a particular problem from WebAssign that actually is talking about filling a swimming pool, but basically the question is boiling down. They ask what is the rate that the pool is being filled in gallons per minute, and that basically boils down to a question of what is the slope of a graph. Given a picture, what is the slope of a graph, of the graph? So let's say I've got this scale where on my y-axis I've got a 10 here, and on my x-axis I've got a 1 here. So each of these tick marks is measured in units of length 1, and this is time in minutes. Well, that's okay, yeah. And then each of these is 10, 20, 30, etc. And this is volume in gallons. Okay, and I've got some line here. Okay, let me put it there. Let me start it there. And I'm going to go through. It's a little bit easier to tell on their picture exactly what point they're going through because they have grid lines. But if I drew grid lines here, I think that would really make my picture look like a mess. Okay, so I've drawn a dot there to show that I'm going through this x value at 3 minutes and this y value up here at 10, 20, 30, 40, 50 gallons. Okay, so how do I find the slope? Well, I use the 2 points that I can see that my graph goes through. The first one, easiest to spot, is right here on the y-axis. That point is 0 for x, right, because it's on the y-axis, and 30 for the y value. And this point, maybe not so easy to note, but once you look at it, and you on WebAssign, there are grid lines, so you can see it goes through one of the grid lines. That's 3, right? 3, comma 50, 10, 20, 30, 40, 50. Okay, so if I want the slope should be the difference in the y values, so 50 minus 30, over the difference in the x values, so 3 minus 0, making sure I subtract this minus this, right? 50 minus 30, 3 minus 0. So what does that give me? That's 20 over 3. I could leave it like that. That would be fine. So I could say 20 over 3 gallons per minute. Now, in the real world, we might like to say, say this as like a mixed number. So we could say, or. Now I'll go ahead and tell you the problem in WebAssign, you just end up getting a whole number. So there's no question about how you should write your answer because it just ends up being a whole number. Now here, though, it's a little bit more involved. So I could write this as, how do you write this as a mixed fraction or a mixed number? How many times does 3 go into 20? 6 times. And how much is left over? 2/3. Okay. So to read slope from a graph, you have to pull 2 points. You have to find 2 points on the graph and then build the slope using that slope formula. Okay. By the way, here's a little weird question. Is f of x equal to 4 a linear function? Technically, yes. Yes, it is. It is. It just, the exponent on the x cannot exceed 1. It can be less than 1. Well, actually, it can be 0 or 1. In this case, this can be written as 4 is equal to 4 times x to the 0. And that's okay. It's still technically a linear function. In fact, like if you define a linear function as literally like it needs to be a straight line, this is still a straight line, right? when you just have f of x equals 4, that's a horizontal line. If you were to graph it, it's a horizontal line at 4. At an output of 4, so I'd say y equals 4. Now, how do you use function notation to graph a vertical line? Well, you can't. Why not? Why can't we talk about vertical lines? That's a good little tangent there. Why can't we discuss vertical lines? Well, because they fail the vertical line test for functions. Throw back to that. What is that, 2.2, I think? They fail the vertical line test for functions. We looked at a few examples of we looked at a few examples of expressions or equations in two variables that described shapes like circles and stuff like that that are not functions because they fail the definition of a function. And a vertical line very much fails the definition of a function because a function is only supposed to output for if you give it an input, it's only supposed to give you one particular output. So if I give it an input of x equals 3, maybe this is out at x equals 3, so 1, 2, 3, then it should only give me one output. But a vertical line, how many outputs does a vertical line give you at that particular value of x equals 3? It gives you infinitely many, right? It gives you a y value here, 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 all the way down here at 0, just infinitely many, right? So it's not a function. Hence, we do not talk about vertical lines in the context of functions. Of course, we can discuss them outside of functions, but not here. All right, what else does this book have? What else do we have here? I think I've done everything else we need to do. Yep. All right. That's it for 2.5.